In this video, we will discuss the concept of electric flux and Gauss's law. Let us begin with electric flux. So electric flux, we denote that with the Greek letter phi. Electric flux is the amount of electric field, penetrating a surface. So the amount of electric field penetrating a given surface is what we call the electric flux. Let us consider this in a more mathematical form. Before we do that, we know that the electric field intensity or the electric field strength is directly proportional to the number of electric field lines, passing through a given area, and perpendicular to that area. Okay, so this tells us that the electric field is equivalent to the electric field lines or the electric flux per given area, phi divided by A. And from here we can conclude that the electric flux phi is equal to the electric field intensity times the area through which the electric flux is flowing. In this equation, we have considered a plane area and an electric field that is perpendicular to the plane of this area. So in that case, the formula holds because the electric field is perpendicular to the plane. The electric field is perpendicular to the plane of the area. Okay, so there we go. Or the normal to the area and the electric field are actually parallel. But this is not always the case. What if the plane of the area is aligned at a different angle to the electric field? So let's have that. Let's suppose we have an area, a certain area that is aligned at an angle theta to the electric field. So that's our area. Then we have an electric field flowing through this area. There we go. Let's suppose the electric field is in this direction. As you notice, the electric field and the plane of this area are actually inclined at a certain angle. Which angle? Let's call that angle alpha. And let's suppose that the normal to this area is this. So I draw a line that is normal to this area, perpendicular to this area. Let me extend this line. And let's suppose that the angle between the normal to this area and the electric field is theta. So in this case, the component of the electric field that is passing through this area perpendicular to it is going to be given by, so this component is E cos theta, and so our electric flux is going to be given by E cos theta times the area. So to make it more general, we have E times A times cos theta, and this gives us the electric flux through an area. As you notice from this equation, if theta is 0 degrees, that means if we have a case where the plane is perpendicular to the electric field, that means the normal is going to be parallel. Normal is going to be parallel to the electric field. In that case, theta is going to be 0, and so we'll have phi as the electric flux as E times A times cos of 0, which is 1. So we have E times A, and in this case we have the maximum electric flux. Also, if we have theta as 90 degrees, that would mean that the electric field and the area are actually parallel, like this. So in this case, this is the normal to the area. There we go. This is the electric field. In this case, the electric flux, which is given by the electric field times the area times cos theta, will be E times the area times cos of 90 degrees, because there's an angle of 90 degrees between the electric field and the normal to the area, and cos of 90 degrees is 0. So in this case, the electric flux through the area is going to be 0, and this is the case where we have minimum electric flux. Minimum electric flux. Okay, let's look at the flux through open surfaces and the flux through closed surfaces. We'll begin with open surfaces. So electric flux through open surfaces. Let us suppose we have an arbitrarily open surface and we have an electric field through this surface. So there comes our electric field in that direction. Now, to avoid the exaggeration, I'll only draw one electric field line to represent all the other electric field lines. So there's our electric field. And let's suppose that it is passing through a certain element of the area. Let's call that area dA. And the normal to that component, to that small portion of the area, is this. I'll draw this in dotted lines. So there we go. This line is the normal to this area. It's a small vector dA. And this is the electric field. Okay. So this is just to name that this is the area. So the electric flux, as we have just discussed, is given by the electric field times the area times cos of the angle between the electric field and the area, cos theta. This can also be written in mathematics using the vector notation as E dot A. This is a scalar product, vector E dot the vector A. So the amount of electric flux, passing through the area dA, let's see what that is. The amount of flux penetrating through a small area dA, let's call that d phi, is going to be given by the electric field E times the small area element dA. So all these are vectors, which I can write as E times dA times cos theta. That's d phi. If I want to find the total electric field through this open surface, the total electric flux phi, I'll have to integrate or to add up all the small areas making up this arbitrary open surface. So I have to integrate over the whole area of d phi. So in that case, my total electric flux is going to be the integral of E times dA, cos of theta over the whole area. So there we go, the integral over the whole area of the electric field dot the small area element. Okay, let's proceed and look at the electric flux through closed surfaces. The electric flux through closed surfaces. So let us consider an arbitrarily closed surface of any shape. Just to emphasize that it is closed, I'll try to make it like this to show that it is three-dimensional. So we have our closed surface here. By convention, the normals to the surface of to the area of a closed surface point from the inside to the outward. So let me consider two small area elements, dA, and the electric field is pointing from the inside to the outwards. So this is the electric field, and this is the normal to the small area element. So this is a vector dA pointing from the inside. The same happens on this side. Oops. So we have the normal. Suppose the normal is this. Then we have the electric field. Also, there we go. So the electric flux is given by the electric flux through a small area element dA, let's call that d phi, is given by the electric field dot the area element dA. Now this is only a flux through a small element. This is a flux through an area element dA. Now if we want to find the total flux through the whole surface, we have to integrate this equation. So in that case, we have the total flux is the integral of d phi, which is going to be the integral. Now this is a closed surface, so we have to integrate over the closed surface. That's very important. So we'll have the integral over the closed surface of d phi, but d phi is E dot dA. So there we go. This is going to be our total flux, the integral over the closed surface of the vector of the electric field dot the vector of the area element pointing from the inside to the outwards. Now we will use this knowledge of the electric flux through closed surfaces to derive Gauss's law. So let's look at the derivation of Gauss's law. So let us look at the derivation of Gauss's law. The derivation of Gauss's law. So for simplicity in our derivation, let us consider a sphere of radius capital R, sphere of radius capital R, having a charge plus Q placed at the center. So let's see what we have. Here we go. We have a sphere of radius capital R. Okay, let's have this of radius capital R having a charge of plus Q placed at the center of the sphere. So in this case, we'll have electric field lines pointing outwards from the charge plus Q, like that. Okay, there we go. So let's also consider an arbitrary element of the area dA with a vector pointing outwards, dA. So there we go. The electric field due to the positive charge placed at the center of the sphere is E. So let's have one line to represent the electric field vector. Okay, there we go. So we know that the electric flux, let's have another color, the electric flux due to electric flux through a small area element, the electric flux through a small area element dA, if we call that electric flux d phi, it's going to be given by E dot dA, which of course is the same as the magnitude of the electric field times dA times cos theta, if theta is the angle between the electric field and the vector of the area element dA. But as you notice from this diagram, the angle theta, so note that the angle theta is going to be 0 degrees everywhere, since the electric field is radial. Since the electric field is radial, so everywhere will have theta as 0 degrees, and so we can conclude that the electric flux through a small area element dA is going to be given by E dA everywhere. So let's find the total flux. If we can find, this is the electric flux through a small area element dA, so let's use this to find the total electric flux through the sphere. The total electric flux through the sphere, so the total electric flux phi is going to be the integral over the closed surface, because this is a closed sphere, so the integral over the closed surface of d phi, which is cos the integral, so we have phi equals the integral of E dA. So this is the integral over a closed surface of E dA, there we go, which is the same as EA, but we know that the area of the sphere is given by 4 pi r squared, and we also know that the electric field intensity due to the charge plus Q is given by Q over 4 pi r squared in this manner. So let us substitute A and E in our equation, see what we have. So E, the integral over the closed surface of E dA, is going to be given by the electric field, okay, which is Q over 4 pi r, oops, there's epsilon naught here, forgot that, 4 pi r squared epsilon naught times the area, 4 pi r squared. So Gauss's law comes out to be, you can see some terms are cancelling here. For example, 4 pi r squared, 4 pi r squared, so we have Q over epsilon naught, and on this side we have the total flux, which is the integral of E dA. Now to make this equation more general, we can have vectors E dot dA, since Gauss's law holds even for configurations that are not necessarily spherical. So this general equation here is what we call Gauss's law. Okay, just put this in a border. The equation here is called Gauss's law. Now Gauss' law is used to find electric fields due to certain configuration where we can achieve the conditions of symmetry. So let's go ahead and look at some of these applications of Gauss's law. Gauss's law is used to find the electric field due to certain configurations which are symmetrical. So applications of Gauss's law. We will use Gauss's law to find the electric field. Due to, so the first one we'll deal with is to find the electric field due to a spherical shell. Spherical shell, that means a hollow sphere. Gauss's law will help us to find the electric field due to a spherical shell, both inside and outside. We'll also find the electric field due to a uniform spherical distribution of charge. So here we're talking about a solid filled sphere. We'll also use Gauss's law to find the electric field due to an infinite line of charge, distribution, and we'll use Gauss's law also, number 4, to find the electric field due to an infinitely large plane. Let us begin with the first one, the electric field due to a spherical shell. So find the electric field due to a spherical shell. Let us suppose we have a spherical shell with a charge positive Q. The charge positive Q is on the surface, and we know that there is no charge inside the hollow sphere, so the electric field inside is going to be 0. So this is the center of our sphere. In order for us to use Gauss's law, we have to introduce what we call a Gaussian surface. Now let's find the electric field inside of the sphere, or inside of the spherical shell. For that case, we will draw a Gaussian surface inside our spherical shell. The Gaussian surface is at a distance r from the center, small r. Let us suppose that the radius of this spherical shell is capital R. There we go. So inside the spherical shell, we mean that, so this is the first case, we mean that the radius of the Gaussian surface is less than the radius of the sphere. So we know by Gauss's law that the integral over a closed surface of E dot dA is given by the total charge enclosed in the surface of area A divided by epsilon naught. But in this case, the charge inside the sphere is 0, so the electric flux E times A is going to be 0, and likewise the electric field inside the sphere is going to be 0. Let us look at the electric field outside the sphere, or outside the spherical shell. In this case, we'll draw a Gaussian surface that covers all the outside of the spherical shell. Let us suppose now that this is a Gaussian surface of radius small r still, so outside the spherical shell corresponds to a radius that is greater than the radius of the sphere under consideration. So by Gauss's law, by Gauss' law, we know that the integral, the closed surface E dot dA, is given by the charge enclosed divided by epsilon naught. In this case, since the electric field is radial and symmetrical, we have the electric field times the area, which is the total flux, is given by the charge enclosed divided by epsilon naught. The area of this spherical surface is 4 pi r squared. So the electric field times the area, 4 pi r squared, equals the charge enclosed in the sphere, which is Q, the charge enclosed in the Gaussian surface. So the total charge inside this Gaussian surface outside here is Q, divided by 4 pi epsilon naught, divided by epsilon naught, this is it. Okay, so also, sorry about this, this is 4 pi small r squared, should have made this clear, 4 pi small r squared. This is the radius of the Gaussian surface, and this is the charge enclosed in the Gaussian surface, so should have made this. So the electric field is given by the charge enclosed divided by 4 pi epsilon naught r squared. This is the electric field outside the Gaussian surface. Now let me plot a graph of the electric field inside and outside. The electric field inside and outside of this sphere. Let us suppose our sphere is here. The sphere is of radius r. Okay, just to make this look like a sphere, I'll try that. Okay, so at this point, this is the radius of the sphere. Inside here is the radius of the sphere, and we know that the electric field inside of the sphere is 0. So our electric field is 0 inside the sphere. Okay, just have that line inside the sphere. The electric field is 0. From here to here is a distance of r, the radius of the sphere. Then outside the sphere, the electric field is inversely proportional to the square of the distance. So it follows the inverse square law, just like that. Let's make it smoother. So the electric field is inversely proportional to the square of the distance from the center of the sphere. So this is the electric field on the vertical axis and the distance from the sphere. So in this case, this is one application of Gauss's law to find the electric field inside and outside a spherical shell. Let us also use Gauss's law to find the electric field due to a uniform spherical distribution. A uniform spherical distribution of charge density. Of course, this is a charge distribution, so it must have a charge density. Let's assume the charge density is rho, coulomb per cubic meter. Okay, so let's sketch what this looks like. We have a spherical distribution. This is a solid field sphere. So there we go. And the charge density here, this is the center of the sphere. Suppose this sphere has a radius r. If we apply Gauss's law inside the sphere, it means we have to draw a Gaussian surface inside the sphere. So there we go, a Gaussian surface of radius small r. We know that by Gauss's law, the total flux E dot dA is given by the total charge enclosed divided by epsilon naught. In this case, the integral over E dot dA is EA, since there is symmetry and the angle is 0 degrees everywhere, because the electric field is going to be radial. The vectors of E and A are actually parallel in this case. The total charge enclosed in this Gaussian surface inside the sphere corresponds to small r less than capital R. So the charge enclosed in the Gaussian surface inside here is going to be the charge density rho times the volume of the sphere, the Gaussian surface, which is 4/3 pi r cubed. Okay, there we go, divided by epsilon naught. So this, the charge density times the volume charge density times the volume gives us the total charge enclosed by this Gaussian surface. Also, we know that the area of the sphere is 4 pi r squared. Sorry, the area of the Gaussian surface, not the sphere. It's very important here when we're dealing with Gaussian surfaces. This A is the area of the Gaussian surface. So let's apply that here. We'll have the electric field. Now this here, the electric field times the area 4 pi r squared equals rho times 4 pi r cubed divided by 3 epsilon naught. In this case 4 pi is going to cancel out on both sides, so 4 pi cancels out. Then r squared cancels out. I only have r remaining here. What else? Okay, that's it. So we have the electric field. The electric field inside the sphere is given by rho, the charge density, times the radius of the Gaussian surface divided by 3 epsilon naught. Notice that inside the sphere, the electric field intensity is directly proportional to the distance from the center. Let's look at the electric field outside the Gaussian surface. So outside the Gaussian, outside the sphere, in that case we have our Gaussian surface outside the sphere. The Gaussian surface is of radius small r, so outside the sphere corresponds to r greater than capital R. There we go. So by Gauss's law, the electric field, the electric flux, over a closed surface is given by the charge enclosed by the Gaussian surface divided by epsilon naught. This is going to be E times A. The charge enclosed by the Gaussian surface is the charge in this whole sphere, which is rho times 4/3 pi capital R cubed. In this case, the charge enclosed by the Gaussian surface outside is the total charge in this spherical distribution, so I use capital R here, divided by epsilon naught. The area, as previously, the area of the Gaussian surface is 4 pi r squared. The small r is for the Gaussian surface, not for the sphere, equals rho times 4 times pi r cubed divided by 3 epsilon naught. Okay, some nice terms are cancelling out here. 4 pi. What do we have left? The electric field is given by rho times r cubed divided by 3 epsilon naught r squared. So notice that in this case, the electric field intensity outside the sphere is inversely proportional to the square of the distance from the center of the sphere, like that. Let's plot a graph of the electric field intensity inside and outside the sphere. So there we go. inside the sphere, we discovered that the electric field is proportional to the distance from the center of the sphere, and at the moment we reach the surface, then the electric field begins to vary as the square of the distance from the center of the sphere. So this is how the graph would look like. From the center to the radius, the electric field is directly proportional. This is our electric field on the vertical axis. This is our center from the sphere, the distance from the sphere. So this is what the graph looks like. From the center of the sphere to the surface of the sphere, the electric field increases with the distance from the center. Outside, when the radius, the distance from the center is greater than the radius of the sphere, the electric field begins to decrease rapidly as the square of the distance from the sphere. So there we go. This is our graph for the electric field intensity inside and outside of our spherical shell. Next, we look at the electric field intensity due to an infinite line of charge. The electric field intensity due to an infinite line of charge. So let's say this is the charge density is going to be, let's suppose it's lambda coulombs per meter. So this is what we have. We have an infinite line of charge, very thin line of charge. Let's suppose it's given a positive charge. So the suitable Gaussian surface for an infinite line of charge would be a cylindrical surface, because it can cover the whole of the infinite charge. It can cover part of this while keeping in mind the laws of symmetry. So our Gaussian surface is going to be like this. Notice in this case we do not have to consider inside and outside, since this is a very thin, I have to mention that, an infinite thin line of charge. So we cannot know what is on the inside. For assume it is very small. So there we go. That's going to be our Gaussian surface. The radius or the distance of the Gaussian surface is going to be small r, and the charge density here is lambda coulomb per meter. Okay, so by Gauss's law, we know that the electric field, the electric flux over a closed surface is given by the total charge enclosed in the Gaussian surface divided by epsilon naught. Since there is symmetry, this is always going to be E times A, the area of the Gaussian surface. In this case, the charge enclosed by our Gaussian surface is equal to the charge density, the linear charge density, times the length of our Gaussian surface. Sorry, that should have been L. So the length of our Gaussian surface, L, divided by epsilon naught. The area of our Gaussian surface, the area of our Gaussian surface is the area of this cylinder, which is given by, okay, the area of the cylinder, 2 pi r times L. So the electric field times the area of the Gaussian surface, 2 pi r L, equals lambda L divided by epsilon naught. As you can see, the length is going to cancel, so that means the electric field intensity. This is nice because the electric field intensity will not depend on that length, so the length cancels out in both. So we have the electric field intensity equals lambda over 2 pi epsilon naught r. So the electric field intensity is inversely proportional to the distance from the line of charge. If I plot a graph for this start out from 0. As the distance increases, the electric field intensity falls in this manner, the inverse proportion of R, not as rapid as that of the charged sphere, but it also decreases. Let us also consider the electric field intensity due to an infinitely large charged plane. So the electric field intensity due to a charged and infinitely large charged plane of charge density. Let's assume the charge density is sigma coulomb per square meter. So let's suppose this is our plane. There we go. It's a very large plane, but we only take this portion. Let's suppose the plane is given a positive charge. For this case, the suitable Gaussian surface would be a cylinder. There we go. Let's assume the electric field intensity to this side is E1 and the electric field intensity to this side is E2. As you can see from the diagram, this is a positively charged sphere, so we have an electric field going this side and another electric field to the left. So in this case, if we apply Gauss's law, okay, here the charge density is sigma coulomb per meter squared. If we use Gauss's law, the integral of E, okay, over the closed surface, so this gives us the total flux equals Q over epsilon naught. Now because of symmetry, this is always going to be EA, but in this case, as you can see, we have the electric field to the right and the electric field to the left. So we have the integral of E1 dA plus the integral of E2 dA, that's the total flux that is penetrating our plane, equals the charge divided by epsilon naught. Let us suppose E1 equals E2, and let's call all this E at once. This is reasonable because this is the same plane, so the electric field to the right and that to the left is ultimately the same. So if we add up all this, we'll have integral over the closed surface of E dA plus integral over the closed surface of E dA equals the charge enclosed in this Gaussian surface divided by epsilon naught. So this is going to be twice the integral of E. Okay, this must have been a vector dA. Just made this mistake. I make this mistake commonly, so just bear with me. Okay, there we go. So the E field dot dA equals the charge enclosed in the Gaussian surface divided by epsilon naught. Let's have more space here. Okay, this is not looking clear. So E dot dA, okay, that's better. So we have twice E times A equals, what's the charge enclosed by our Gaussian surface? Well, that's the charge density times the area of our Gaussian surface, which is in that case A, divided by the epsilon naught. As you can see, A cancels on both sides. Now this is one nice thing with Gauss's law, that every time there is symmetry, then the unknown term is always going to cancel out. In this case, it is very difficult to know what that area would be, but we can easily cancel that out so that we get a generalized equation. So we have 2E equals sigma divided by epsilon naught. Our electric field intensity is going to be sigma divided by 2 epsilon naught. So this is the electric field intensity due to a charged infinitely large plane. We could also find the electric field intensity due to parallel plates, which perhaps we'll do. So let us calculate the electric field. The electric field due to two parallel plates, okay, due to two infinitely large parallel oppositely charged plates, of charge density sigma coulomb per meter squared. So previously we have looked at the electric field intensity due to an infinitely large plane or plate. So if we have a plate of this kind, infinitely large, we say the electric field intensity due to this side and due to this side, the electric field intensity, if this is this is a positively charged plate, we have considered this in our previous video, the electric field intensity is going to be sigma divided by 2 epsilon naught. Even this side, the electric field intensity is going to be sigma, sigma over 2 epsilon naught. So this is what we have considered in our previous video. Now let's have two planes of this kind, or two plates. So we have one plate here, another plate here. So there we go. These plates are infinitely large, but we only consider this for purposes of not exaggerating the diagram. So let's suppose this plate is positively charged and this plate is negatively charged. Okay, just have a different color for that. So the electric field due to the positive plate is going to be, so this, the electric field due to the positive plate, we use the blue color, is going to be sigma over 2 epsilon naught. Also outside on the other side, the electric field due to this plate is still going to be sigma divided by 2 epsilon naught. The electric field, also this side, the electric field is going to point to this direction, sigma over 2 epsilon naught. The electric field due to the negative plate is going to be pointing towards the plate itself, so it's going to be, so we suppose the charge density is sigma in all cases, so it's sigma over over 2 epsilon naught. It also points towards the plate here, so I have sigma over 2 epsilon naught. It points towards the plate, not outwards. Recall that electric field lines point from the from the positive charge and then to the negative charge. So that's why we have a configuration of this kind. So sigma over 2 epsilon naught. Now let us find the resultant electric field intensity at this point. If you add this plus this, since they are in opposite directions, the electric field intensity here is going to be 0. The electric field intensity is going to be 0 in this region. In between the plates, we have sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So there we go. Sigma over 2 epsilon naught plus sigma over 2 epsilon naught, because they are in the same direction. So perhaps I can take off this, it's not important here. So we have our resultant electric field intensity in this region as sigma over epsilon naught. On this side also we have this sigma over 2 epsilon naught in this direction to the right. We have sigma over 2 epsilon naught to the left, so the resultant is going to be 0. So we only have the electric field in between the plates. On the other sides of the plates, we do not have an electric field. Notice that this electric field applies well inside the sphere, the plates. So if you have two parallel plates, a positive plate and a negative plate, the electric field inside here is sigma over epsilon naught. That is, as long as you're inside, well inside the plates, the electric field is going to be that. Okay, but towards the surface, towards the end of the plates, the electric field is going to be a little different. So this electric field is inside the plates in the middle here, but as you come towards the edges, the electric field intensity becomes a little bit bizarre. Okay, so this is all for the electric field intensity due to two infinitely charged oppositely parallel plates. And all these are some of the different applications of Gauss's law. Notice that we are able to deduce this result from our previous derivation of the electric field intensity due to a charged plate using Gauss's law. Okay, if you're watching this on YouTube, please don't forget to subscribe to this channel. Also leave a comment, leave suggestions for future videos, and I'd really appreciate if you help us to grow this channel by sharing with friends. Okay, see you till then.